not. Maybe we... Okay, here we go. All right, we are recording. So, like I said before, everyone, today is a test review. Your test is on Wednesday. It should all be on Canvas, the multiple choice and the problem set portion. So let's go over the exam. And like I said, I'll go over this pretty fast because I feel like there's a lot of material to cover. The first thing I want to tell you is that this is going to cover Chapter 15 and 16. And Chapter 15 deals with acid-base chemistry. So as an example, you'll be asked to find the pH of an acid. So first of all, the pH is minus the log of the hydrogen ion concentration. So it's a scale. So as a scale, if your pH is equal to 7, you are neutral. You're not either acidic or basic. But if your pH is less than 7, kind of like the insides of our stomach, then there is more H plus than there is OH minus in concentration, and we call that an acidic solution. And then finally, if your pH is greater than 7, pH 8, pH 9, pH 10, pH 12, then your solution is basic. That's what we call it. That is the opposite of acidic, where you have more OH minus hydroxide ion than you have H plus. So make sure you know acidic, basic, and this one where they're equal to one another, that solution is going to be neutral. So a multiple choice question on this. And of course, also please remember that pH plus POH is equal to 14. Okay, so make sure you know that very simple mathematical relationship. That lowercase p in pH stands for power. So it's minus the log of whatever it is you're taking the power of. So we can do the same thing. POH would be minus the log of the OH minus concentration. We call that the power of OH. We can do the same thing with Ka. So there's something called pKa. If you go deep into chemistry, there's a lot of information about pKa. That's the power of the acid equilibrium constant. So it's going to be minus the log of Ka. And then the power of Kb. Okay, how well is a base, weak base, how well does it give off OH minus? Weak acid, how well does the acid give off H plus? The pKb is just nothing more than minus the log of Kb. All of these entities here, pH, POH, pKa, pKb, are unitless. So they really have no units. Also, I should say Ka, Kb, these equilibrium constants. We also talked about another equilibrium constant called Ksp. Anytime you have an equilibrium constant, capital K, that is also unitless. Okay, so this is information that you can get multiple choice questions from, so make sure you know that. In terms of mathematics, we have a pH of a strong acid versus the pH of a weak acid. So a pH of a strong acid, there's 6 of them. So as an example, the pH of a concentration of 0.475 big M HNO3. HNO3 is a strong acid, you see. So anytime you see HNO3, this is called nitric acid. If you see HNO3, if you see sulfuric acid, if you see HCl, hydrochloric acid, if you see, we don't talk about this much, but this is called perchloric acid. The halogens, HBr, HI, along with what we've shown here, HNO3. These are strong acids. So they are a very much close to 100% source of H plus. So if the question is asking you what is the pH, the question is asking you what is the pH of a 0.475 molar solution of nitric acid, or any of these acids, any of these 6, what I call them, you just plug it straight in. Okay, you just plug it straight into your pH equation, and that will give you the answer. Okay, because these are 100%, or very, very close to 100% going to give you H plus. Very close. So just plug it in. Okay. Now, if I say what is the pH not of a 0.475 molar solution of HNO3, but if I say what is the pH of a 0.475 molar solution of something like HCN, which is called cyanic acid, you cannot plug it straight in. Okay, why you cannot plug it straight in? You cannot plug it straight in because it's a weak acid. So for that, you have to write an ice table, and you have to write the equation. So for this one, the equation, make sure you know this equation, not just for a cyanic acid, for any weak acid. You can't plug it in, first of all. You cannot plug in straight to this equation because it's not a strong acid. It's a weak acid. So two things here. One is you'll have to know the equation for all these weak acids. Acids do what acids do, and they give off H+. And acids will produce H+. Okay, I'm writing H+ in the form of H3O+, but you can also write it in the form of H+. So I want you guys to recognize the way I'm teaching this to you, H+ and H3O+ are one and the same thing. I use them interchangeably. And also, you're going to get Cn-. Everything is dissolved in water except water. Water is a liquid. So that's the first thing. If you're asked a pH of 0.475 or whatever number they throw at you. Another thing that has to be given, or I'll have to give this to you, or I'll throw that question out. I have to give you a Ka. Okay, so this tells us to what extent this reaction is going in the forward path, the forward direction. Now, figuring out the pH of 0.475 molar HCN is just using an ice table. So it's going to be 0.475 here, ICE. Initially, we won't have this. Initially, we won't have that. Some of that cyanic acid is going to go this way, and this is just straight up using your ice table, plus X, plus X. For a lack of time, I'm just going to tell you what to do next. Now, this gets plugged into your Ka, right? Your Ka is products over reactants. No solids and no liquids whatsoever. You can plug in the numbers here. I will not go over the math just to save some time, but it's going to be 4.93 times 10 to the minus 10. At equilibrium, the H3O concentration is X, the Cn concentration is X, so X times X is X squared. And at equilibrium, some of it is going to go this way. The equilibrium concentration is 0.475 minus X. Okay, from here on out, you can use the low ionization assumption. Okay, so you don't have to use any quadratic on this exam, but you will assume X is small, whereby 0.475 minus X is about 0.475. And then you can go on and solve the problem from there. Okay, so. Alright, so the key point here is that pH of a weak acid goes in ice table, or gets in ice table. The pH of a strong acid, you can plug it straight into your equation. Okay. Right, and then you'll have to do the math here to find X. X is your H3O concentration, and then from there you can plug that X into your pH equation. Okay, but to save time, I'm not going to complete this problem. Can we move back and forth between pH and concentration of H3O plus? Can we do that? Here's what I mean by that. We get a pH which is unitless, but really it's the power of your H plus, your H3O plus concentration. pH by definition is minus the log of the H3O plus concentration. But can we go back and forth? As an example, if you have a pH of 6.93, let's say our pH is 6.93, okay? What is the H plus concentration in moles per liter that corresponds to this pH? Okay? So here, to solve for that, here's our equation in terms of pH, but I want to do kind of the opposite. I want to figure out what is my H3O plus, or what is my H plus concentration. So the formula for that is 10 to the power of minus pH. 10 to the power of minus pH. So answering this question here, the H plus concentration, notice I'm using them similarly, interchangeably, is going to be 10 to the power of minus 6.93. On your calculator, that's the anti-log. So look at your log button. You're not going to do log, but you're going to do the button that's above the log. So shift log 10 to the power of minus 6.93. Minus 6.93. Close those parentheses. And here it's about 1.17 times 10 to the minus 7. Also, you want to put units here. Okay, units. This gets units, and the units are concentration moles over liter. Units. While pH does not have units, the power of H does not have units. The H plus concentration does have units, and the units are moles over liter. So make sure you're comfortable, in essence, going back and forth between pH and hydrogen ion concentration. Okay, another question on the exam has to do with the Ksp. Okay, Ksp stands for the solubility product constant, and it's used for sparingly soluble solids. Okay, solids that are in equilibrium with their component ions. As an example, here's a sparingly soluble solid. It's called lead iodate. It's a solid that's in an equilibrium, so this is called lead iodate. You don't really need to know the name of it. But can you write the equation of Ksp for lead iodate? Okay, that's something we should know. It's going to be Pb plus 2 aqueous plus the iodate ion, IO3 minus aqueous. We always want to balance. This is called the iodate ion. Way back when you had me in a Chem 1, I actually made you do some flashcards. One of the flashcards is the iodate ion. So this is something you should know, the equation that defines the Ksp for this sparingly soluble solid lead 2 iodate. Another thing is I have to give you a Ksp. So the Ksp, we get it from a textbook, or we look it up. And it's not something you memorize, but it's 2.5 times 10 to the minus 13. Okay. Usually this is given at a specific temperature. Right, how does this work? It's an ice table, okay, because we have that back and forth arrow. Some of that solid is going to give away its ions to water, okay, because all of this is in water. This is not 100% a solid, but some portion of it will go back into lead plus 2 dissolved in water and IO3 minus dissolved in water based on this Ksp. So in order to do that, we're going to do our ice table. So this is going to be plus S, and you see this will be plus 2S. A lot of people forget that. Okay, so don't forget this is plus 2S. Our Ksp, like any capital K, is products over reactants. So here the product is Pb plus 2, and here the product is IO3 minus. We have to square it. Okay, this is another thing that students in their rush mess up on. You have to square it. And now we'll plug in our equilibrium values. Ksp is a constant that I will give you. It's 2.5 times 10 to the minus 13. At equilibrium, something that goes this way, we'll call that S. Whatever extent this goes this way, S. The S stands for solubility. For Ksp, we're talking about solubility. How much of that solid gets dissolved back into water. At IO3 minus, at equilibrium, is going to be 2S, and then we have to square it. So this is 4S squared. This is S. So this will be 4s cubed equals to 2.5 times 10 to the minus 13. Okay. We solve for s, and this is going to be 2.5 times 10 to the minus 13 divided by 4. We cube root that to isolate s. If you don't know how to do cube root on your calculator, what I usually do is, this is the same thing, 2.5 times 10 to the minus 13 divided by 4. You raise that to the 1/3. Instead of raising it to the 3rd power, you raise it to the 1/3 power. Okay, so these two are the same. These give you the same answer in terms of solubility S. So if we do that really quickly, 2.5 times 10 to the minus 13 divided by 4. Okay, I'll raise that to the 1/3 power, if you're following along. The solubility is about 3.97 times 10 to the minus 5, big M. Okay, big M. Units here are big M. Now the question may ask you, what is the solubility not in big M? But I may ask you, what is the solubility in grams per liter? Okay, not in moles per liter, but grams per liter. Okay, grams per liter. This is easy, so don't get flustered by this. It's going to be 3.97 times 10 to the minus 5. This big M is moles per liter of lead iodate. To get it to grams per liter, because big M is moles per liter, for every 1 mole of lead iodate, you have this many grams, and that is just a molecular weight. You get it from the periodic table. Okay. Lead plus 2I plus 6O. Okay. That is how many grams, molecular weight in grams. And that will give you the solubility not in moles per liter, which we calculated up above, but in grams per liter. So, if you have 1 liter of the solid, if you have 1 liter, how many grams go into that liter?
What is the number of grams?
Sorry?
The number of grams.
Molecular weight.
Okay.
From the periodic table. So whatever lead is on the periodic table, I don't think I have a periodic table with me. But you just read up that number from the periodic table. Okay. Why did I multiply I by 2? Because I got 2 I's. Why did I multiply oxygen by 6? I got 6 oxygens. Yeah. Oxygen is 16. Oxygen is 16. Iodine is, you can look it up in the periodic table. Oxygen is 16.01. Iodine is Iodine is 126.90. Oxygen is 15. And lead is 207.20. So you'll have to add them up. Okay? The molecular weight. And that will give you the answer in units of grams over liters. right, here we have a Ksp equation. What about a Ksp equation in terms of the common ion effect? Ksp illustrating the common ion effect. So here I'll give you an example of AgBr. This is also a sparingly soluble solid. It's at an equilibrium with its ions Ag plus Br minus. Anytime you have a Ksp, I have to give you the Ksp value. The Ksp value is 5.0 times 10 to the minus 13. We look it up, and it's something I'll give you. Do not have to memorize it. But I'm going to ask you this question. Here, you see, if everyone looks, this is the solubility in water. What if I ask you, what is the solubility in .015 molar NaBr? Okay. So not the solubility in pure water, but the solubility in water that contains dissolved NaBr. Right, so this is the common ion effect. NaBr is nothing more than Na plus and Br minus. All right. So let's do our ice table one more time. Okay, so this is going to be plus S. Make sure it's balanced. Make sure our Ksp equation is balanced. This is S. This is S, the reaction that's going this way. But what else is it also? Where's the Br minus coming from? You see there's two sources of Br minus. What's one source? One source is the reaction going this way. Okay, what's the other source of the Br minus? The other source of the Br minus is the NaBr, because remember, the solid is not going in this direction in water. It's going in this direction, in 0.015 molar NaBr. Everyone see that? So there's two sources of Br minus. One is the reaction literally going to the right, and the other is the Br minus coming from this solution. So it's going to be S plus 0.0105 as our Br minus concentration. So we can do our Ksp again. It's going to be Ag plus times Br minus. Ksp will be given to you. I looked it up. It's 5.0 times 10 to the minus 13. Ag plus is S. Br minus is S plus 0.015. And then we can solve for S. Here I would assume S is small. Okay. Assume solubility S is small. So very little of it is going in this direction, and most of the Br minus is 0.015 molar. Okay, that's the source of the Br minus. Very little of the source of the Br minus is from this reaction going in this direction. It is some, but it's a small amount. Again, 5 times 10 to the minus 13 is so small. So doing that, it makes the math a little bit easier. And then here you can solve for S. That will be the answer, whatever that is on your calculator, and the units are going to be molar, moles over a liter. Okay, don't forget the units. So there's a problem where you have to use the common ion effect for a Ksp. So one question I want to ask you guys, the common ion effect, here highlighted in orange, will that increase ionization or decrease ionization? Increase or decrease ionization? So here we have Br minus, that's 0.015, plus the reaction of Br minus that's going this way. So will this increase ion formation or decrease ion formation? You're having more ions, so what will that do to the reaction? Will that increase, make the reaction go this way, or will it make the reaction go that way? If you add more ions, which way will the reaction go? Common ion effect. So here we're having it, and it's not in water now. It's in sodium bromide. So what you have in your solution, you have Ag plus, you have Br minus, and you have the Br minus from the 0.015 molar Br minus. So you have more Br minus. You add the common ion, right? Circling the common ion here. The common ion Br minus from NaBr, and then we have the common ion present from the reaction going this way. So we're having more ions. According to Le Chatelier's principle, which way will the reaction shift? Left or right? Right. So will that increase or decrease ionization? We have having more ions. We have this as an ion, Br minus. We have Br minus from this reaction going this way. So more ions, the reaction will counterbalance it, so you will have less ions and more solid formation. So the common ion effect will decrease ionization. Because you have the common ion here, it's Br minus. More ions, the equilibrium will counterbalance that, so the reaction will actually give you more precipitate. Okay, will give you more precipitate, as opposed to just in plain water. So here above we did it without any common ion. This is just in plain water. Here we're doing it with the common ion. The problem tells you it's in 0.015 molar sodium bromide. With the addition of the common ion, with the addition of more Br minus, the reaction is going to go this way. Okay, that's just Le Chatelier's principle. All right, there's a section on the exam where you have to rank acids. So, ranking acids. So, as an example, which is the stronger acid, H3PO4 or H2CO3? Okay, so here you want 1 being the strongest acid, and then 2 being the weakest acid. Okay, like that, you can go all the way up to 5. So rank them 1 to 5. But I'm only going to give you 2 in this example, but on the exam you'll have to rank 5 of them. So, which is the strongest acid? Well, there's more information that needs to be given. Here, the pKa of H3PO4 phosphoric acid is 2.12. And here, carbonic acid, okay, this is found in our bodies, by the way, carbonic acid, H2CO3, is 4.3 times 10 to the minus 7. And given that data, which is stronger and which is weak from this pair? Or ranking them. First thing I would do is get them into the same, get them either all in pKa's or get them all into Kas, right? So let's get them all into pKa. So pKa here is 2.12. Or I could get them all into Kas. Just get them into the common metric. Bless you. Bless you. And so I'm going to have this convert that to pKa. So pKa is minus the log of Ka. Minus the log of Ka. So Ka is 4.3 times 10 to the minus 7. And that's 6.37. So here we have a pKa of 6.37. So now I got them all in pKa's. I could have all gotten them in Ka's also, but I'll just get them all in pKa's. So which is the stronger acid? Okay. So here's how that rule works. I think you got the right answer there. You see, the higher the Ka, because of the formula, it means lower the pKa. That means the stronger the acid, right? So here I got them all in pKa, so this would be the stronger acid. I'm sorry. This would be the stronger acid, number 1, H3PO4, and 2 would be the weaker acid. So this is what you want to know. The higher the pKa, the weaker the acid. The lower the pKa, the stronger the acid. Or I can say equivalently, the larger the Ka. Remember, if I have $1 million, am I moving forward or backward? If you have $1 million, if your Ka is 10 to the 6th, then you're a really strong acid. So like that, you're going to have to rank 5 of them. All right. So here I ranked 2 of them for you. You can rank the 5 of them. 1 is being the strongest, 5 is being the weakest. Okay, another thing that's on the exam is this idea. This is also on your problem set. Understanding and identifying conjugate acids with the conjugate base. So if I give you, let's say I give you something like this, HCO3 minus, or maybe CO3 minus 2, what would be its conjugate acid? And to get its conjugate acid, you add an H plus to it. Okay, so adding an H plus to this will give me H2CO3. Okay, no charge. Adding an H plus here will give me HCO3 minus. Okay, minus 1 charge. Everyone see that? How about if I tell you H3PO3, phosphorus acid? What would be its conjugate base? Not conjugate acid, but conjugate base. Here we don't add an H plus. Here we remove an H plus. So the conjugate base of this would be H2PO3, and then because you removed the H plus, it gets a minus. So conjugate acid, conjugate base pairs. All right, so make sure you can identify them. You want to do one more? What is the conjugate base of sulfuric acids? One of our strong acids, one of our 6 strong acids. What do you do if you want to get the conjugate base? You remove an H plus. So I'm removing an H plus. This becomes HSO4. Do I have to put in a charge? minus. So here we're removing an H plus to get the conjugate base. Here we're adding an H plus to get the conjugate acid. All right, so this will be on the written portion of the exam. And also maybe a couple of questions on the multiple choice. All right, finally, a couple more things here. Titrations, okay. Titration problems. So let's say you titrate a weak acid with a strong base. Okay. That is, you have a strong base and you drip, 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 drip. You drip it to a weak acid. So here's an example of a weak acid. It's acetic acid. And here's an example of a strong base, sodium hydroxide. Okay, I'm just going to put OH minus because the sodium Na plus is really just a spectator ion. So if you titrate OH minus with acetic acid, here's the equation that you will get. You see OH minus is a super, super strong base. It's going to take, it's a grabber. It grabs H plus. Acetic acid gives H plus, but it gives it very weakly because it's a weak acid. But this is the equation you'll get. Okay. H2O is always a liquid. And you get the conjugate of this, which is acetate ion. So let's say you have a typical question, what is the pH? Okay, and what is the pH if you have 40 milliliters of acetic acid whose concentration is 0.0100 big M? And you add to that 10 mils of OH minus, and its concentration is 0.020 big M. So what is the pH of such a mixture? Okay, this would be what's called a titration. So first thing, you'd get the final concentrations, OH minus. You have 10 milliliters of a 0.20 molar concentration divided by, after mixing, the total volume will be 60 milliliters. And whatever that is on your calculator, the mils cancel. So 10 times 0.02 divided by 60. I'm getting 0.0033 M. Our concentration of acetic acid. Okay, well, we had 40 mils, and the concentration is 0.0100 big M. When we mix these two in the titration, the total volume will be 60 milliliters. Okay. So the mils cancel, leaving us with big M. And this would be 0.00667 big M. So this is our concentrations. And then we can go ahead and plug that into the ICE table. So our concentration of OH minus is 0.0033. Our concentration of acetic acid is 0.00667. Okay. Okay, water is a liquid, so don't care about that. All right, the reaction is going to go this way. How much OH minus is going to be eaten up? Okay, here's a hint. It's a strong base. So how much OH minus will be consumed? It's a strong base. All of it. All of it. But how much is all of it? All of it here is 0.00333. 0.00333. All of it is the right answer. All of it in this specific problem is 0.0033. And all of it, that's 0, and then this is going to be leftover 0.00, what is that, 334 or something like that. All right. So to get the pH, what we would use is the Henderson-Hasselbach equation. Okay, so the pH here is equal to pKa plus the log of, drop the acid, so acid is in the denominator, CH3COOH, and then in the numerator is the conjugate base. So the Ka, I believe, for this is 1.75 times 10 to the minus 5, the Ka for acetic acid for this pair. And then you can go from there to solve for the pH. All right. So in the interest of time, I'm not going to solve it. So this is one type of problem. But let me ask you this. Another problem that will appear on the exam is what will be the pH, let's extend this, at the equivalence point. Okay, what will be the pH at the equivalence point? So that's a whole other issue here. So let's see if we can solve for that here. So at the equivalence point, what will you get? Let's do the exact same problem. We have our weak base. We titrate it with some strong, we have our weak acid. We titrate it to our strong base. And we're going to get H2O water. Bases will pick up that proton really, really good. Weak acid will give off that proton really, really weak because it's a weak acid. And equation just from last time. But this time we want to ask ourselves the question, what is the pH at the equivalence point? So let me throw in some different numbers at you guys. So let's say we have 100 ml times the volume, and the concentration in the bottle is 0.10 molar. And here we have OH minus, the concentration in the bottle is 0.25 molar. Come on, don't get blurry on me. Still got a lot more to go. Right. So here, if you guys can see this with me, we have a volume and a concentration. Here, the OH, we just have a concentration. So what volume of this concentration can totally neutralize this? All right, so here we'll use M1 V1 equals M2 V2. So we have 100 milliliters of the acetic acid. The concentration in the bottle is 0.10 molar. Here the OH minus, they just tell us the concentration is 0.25 molar. Okay, but how much of that 0.25 molar will completely and totally react with this volume at this concentration of acetic acid? All right. So on my calculator, I think this is about 40 milliliters. Okay, so solving for V1, you get 40 milliliters. Right, so now with that being said, we can figure out our concentration. It takes 40 milliliters of this 0.25 big M OH minus to completely neutralize the acetic acid. So our final concentration of OH minus, it's the equivalence point, so they will all be the same. Titrant and titrant will be the same. So we have 40 milliliters. The concentration is 0.25 molar. Our total volume is 100 plus the 40 will be 140 milliliters. So here the mils cancel, and the concentration will be 0.0714 big M. CH3COOH, acetic acid. Here we are starting out with 100 milliliters of a 0.10 molar solution. Total volume after we add this 40 milliliters of this OH minus, the total volume will be 140 ml. The ml cancel, and would you not know? It is the equivalence point, so obviously it's going to be the same. Now, what happens when you do your ice table is the issue here. This is what makes solving the pH at the equivalence point a little bit of a challenge. Let me rewrite this equation here. Okay, so here we have the OH minus is 0.0714. Here the CH3COOH acetic acid is 0.0714. How much OH minus will be consumed? All of it. It's a strong acid, but how much is all of it? Very good. Now we have a problem. Okay, now we have a problem, and this problem only occurs if you are at the equivalence point. How will we get the pH? Have to use the back reaction. Okay, so let's use the reverse reaction here. Acetate is a weak base, so it's going to pick that up. And water is a weak base. It will donate that proton. What is this to you guys? Is this Ka? Or what is that? We're making OH minus. Water is a reactant. Is this Ka? Ksp? What type of K is this? This is the equation that's going to signify or symbolize Kb. Kb. How will we get Kb? This is something you'll need to know for the exam. Kb can be solved for by this equation. So Kb is equal to Kw divided by Ka. Okay. Kw is 1.00 times 10 to the minus 14. Ka, I'll give you Ka, it's 1.75 times 10 to the minus 5 for acetic acid. Okay, now you can do your ice table as done before. Minus x plus x plus x. And this will be 0.0714 minus x. This would be plus x. This would be plus x. Right, so Kb is going to be OH minus times CH3COOH divided by CH3COO minus. Okay. So OH minus is x, CH3COOH is x, x times x is x squared. Kb is whatever this number is, I don't know off the top of my head. Kb is going to be x squared divided by 0.0714 minus x. And here we will assume x is small. You can, on this exam, you can always assume x is small. So 0.0714 minus x is about equal to 0.0714. If you solve for x, what will you get? Will that give you OH concentration, or will that give you H plus concentration? OH concentration. So will we calculate pH or POH first? We will calculate POH first. How will we get to pH? 14 minus that. Okay. This only happens at the equivalence point. After the equivalence point, actually you're going to have more OH minus, but that's all. All right, make sure you know how to write a Kb equation. I think I have time is running out for me. Make sure you know how to write a Kb equation. Okay, so as an example, Kb for something like this, C6H6COOH. Well, you may never have seen such a thing before, and that may freak you out. But don't worry, it's asking you write the Kb. So all you got to do is write the Kb. Okay, water is always involved. And the Kb is going to produce OH minus. Just like the Ka reaction produces H plus or H3O plus, the Kb is going to produce OH minus. Something like this. Okay, so C6H7OOH plus. So just as you know, just as you know how to calculate or write the Ka reaction, I'm just saying make sure you know how to write a Kb reaction. Okay, as an example, here's our best Kb reaction. Ammonia plus water. Ammonia is actually a very weak source of base, so here's your standard Kb reaction. So another example of a Kb reaction. All right, one final thing I'm going to mention here is, and then I think I have to go, it's way past time. We have to do a Q versus Ksp problem. This is in our problem set. So as an example, if you have the sparingly soluble solid calcium fluoride, this is in an equilibrium with calcium ion plus fluoride ion. Okay, let's balance this equation. And let's say that the calcium ion in the form of calcium nitrate, you have 0.100 liters solution, volume, and the concentration is 0.300 molar. Okay, so this is your source of calcium ions. Let's say I have sodium fluoride. And the sodium fluoride, I have 0.200 liters, and the concentration of sodium fluoride is 0.060 molar. Right, so the question is, given this concentration of calcium nitrate, which is a source of calcium ion, given this concentration of sodium fluoride, which is a source of fluoride ion, will a precipitate form? Okay. So first you have to write your Ksp equation. Okay, this is going to be plus S plus 2S. And then your Ksp is going to be calcium ion plus F minus squared. Does this ring a bell to everyone? As best as possible. Calcium ion is plus S. Fluoride ion is 2S, but we have to square it. Okay. The Ksp is whatever it is in the book. And then you're going to compare this value to Ksp. Okay, so here you're going to put Q first, and then use the alligator rule. Okay, if it's greater than, you're going to get a precipitate. If it's less than, these two will not precipitate out, it will still remain in solution. Does everyone know how to do this type of problem? Right, you got to figure out your calcium ion concentration, and then you got to figure out your fluoride ion concentration. All right. Everyone know how to figure out your final concentration? Calcium ion is going to be 0.100 liter times 0.300 molar. Our total volume, 0.1 plus 0.2, is going to be 0.300 liter. The liters cancel, and then you're left with the concentration of calcium ion. You'll do the exact same thing for the fluoride ion, and then use this Ksp equation. See if it equals Ksp. If it equals Ksp, then it's a saturated solution. But more often than not, it will either be Q will either be greater than Ksp or less than the actual Ksp. In that case, you will figure out and determine whether it will be a precipitate or not. All right, so these are the type of problems that you will see on Wednesday. And I'll have some office hours Tuesday night through Zoom if you want to get any more clarification. But I think I'm way overboard and I have to go to another lab.